Hi, Dr. Hugger.
Hi there.
Today we're going to talk about the golden ratio and see some ways that it's in our world around us.
Okay.
Okay. So, first of all, recall that the golden ratio is the number.
It's a fixed constant, never changes, right?
Yes.
Just like pi?
Yes. So we use a Greek letter phi to represent it.
Okay.
It's precisely equal to the ratio, the quantity 1 plus the square root of 5 divided by 2, or approximately 1.618.
Okay, got that.
So with this set of golden ratio calipers, Dr. Hugger, we can see their measurement by comparing the length of the calipers to a ruler. Okay. So let's open the calipers such that the outer arms go, you'll have to help me over there, I can't see.
You got it. So
go to about 16 inches.
16 inches.
And then notice these first and second arms meet at about 10 inches.
I can see that.
So the whole length, 16 divided by 10.
Is about 1.6 roughly. That's what we're going for.
Okay.
Okay.
All right. So I'm going to show you where this golden ratio appears in your own body.
Oh, okay.
Hold out your right arm for me, if you will. Okay, so I'm going to open the calipers such that the two wider arms go from your elbow to the tip of your longest finger. And notice where that middle arm meets.
It's right at the wrist.
Right at the wrist. So if we take that entire length from your elbow to the tip of your finger, divide it by the length of your forearm, we get about 1.618.
Wow, okay, strictly average. That's me.
All right. Most people, that is the case. Hold out your hand now.
Okay.
And let's look at that hand where we can see this golden ratio appearing. Let's measure the length from your wrist to the tip of your longest finger and compare that to the length of your finger. Again, we're hitting at about 1.618.
Okay, so the hand divided by palm, right? That should be the golden ratio.
Yes.
Cool.
All right. So the golden ratio also is used to define what we mean by a golden rectangle.
Right.
A golden rectangle is any rectangle where we measure its base length and its height length. We take base divided by height, and we get the golden ratio.
That's right. Okay.
In your textbooks, most students saw the example of the Parthenon meeting the golden ratio. If we take the base length of this Parthenon divided by its height, we get the golden ratio.
Sure.
And additionally, if you start with a golden rectangle, you can always subdivide any golden rectangle into a square and a smaller golden rectangle. So notice here, we've divided the entire outline of the Parthenon into a square and a smaller rectangle. This smaller rectangle is also a golden rectangle. And you can keep that process.
I love that. Yeah, you pretend you're like cutting off perfect squares and always the leftovers are a golden rectangle. And then you cut off another square, you have a golden rectangle. You cut off another square, you have a golden rectangle. It can go forever. And
you can see that with the calipers. So if we hold them up, the two outer pieces going from the outer corners of the Parthenon, then this distance is approximately, we could use that as our unit of 1, and the entire length there is 1.618.
Oh, fantastic. And then it works again.
And then it continues here again. Okay, we put that unit 1 on the square, and then the entire length has a ratio of 1.618 to that square length.
That's neat.
So that's what a golden rectangle is. Additionally, there are golden spirals, and a golden spiral is a spiral that gets wider by the golden ratio with each quarter turn.
Okay.
You could see this by inscribing the spiral within a golden rectangle and then subdividing that golden rectangle into a square and a smaller golden rectangle. Let's see what you have there.
That's how I learned it. That's why I love that property of like cutting off squares forever, because that's the property that you use to generate a golden spiral, right?
Show us how you draw yours.
Oh, I love it. Okay, so we have like the square, right? You know, you can always cut off a square and what's left over is a smaller golden rectangle. So instead of trying to figure out where the spiral goes, a little hack is you draw this 1/4 circle, right? Lower left to upper right. Instead of trying to turn your brain around, you turn the paper. And then you draw another quarter circle, and then you turn the paper, and you draw another quarter circle. And you can keep going as long as you have drawn good enough golden rectangles, right? Eventually you're going to have to stop. But technically, this golden spiral spirals around infinitely many times, right? So anyway, that is a nice little trick for drawing pretty golden spirals, in case you get confused.
Yes, and again, we can use our handy calipers and see that relationship. The length of that square, let's say, is 1 unit. The total length of this outer rectangle is 1.618. Flip it one time. Let's see if we still see that. Okay, there's another square and a golden rectangle. Again, we see the same. All right. These golden spirals also occur all over the place. Seashells, hurricanes, galaxies.
Hurricanes. When you see like the satellite images of hurricanes, they make like a spiral shape.
Yes. We have an example of Hurricane Sandy. which was the deadliest and most destructive hurricane of the 2012 Atlantic hurricane season. It was the second costliest hurricane in U.S. history. This particular satellite image of Hurricane Sandy shows that it follows a golden spiral pattern. Let's use our caliper. And I've overlaid on top of the photograph the subdivision of the squares and golden rectangles. Right. Again, we can open up our calipers and see that measurement.
I love that.
Okay, so we hope you've become more aware how mathematics is all around us in our daily lives, and we encourage you to look for patterns and mathematical structure all around you.